Good morning, everybody. Good morning. We would like to start. And I remind you once again to switch off your phones. I'm very pleased to open this first session of the sixth Asian Science Camp on behalf of the organizers. You know, this is the first time this Asian Science Camp takes place in Israel, in this marvelous campus of Edmond J. Safra of the Hebrew University in Jerusalem. This is also the first time we include in the mathematics is included in the program on top of biology, chemistry, and physics. It is probably most appropriate to start this session, this first session, with these two new aspects, both Israel and mathematics, by words of the most appropriate person who is professor of mathematics at the Technion, and at the same time the Israeli Minister of Science and Technology, who will greet us all on behalf of the Israeli government. Professor Daniel Hershkovitz, Minister of Science and Technology in Israel. Is he here? He should be somewhere. Okay, we will wait for him for a moment. Let me just say that after his words, we will have short intermission, musical intermission, by Orel Oshrat, who will play a piece on piano, a piece he composed by himself. And later on, we will start the first lecture by Professor Yuan T Lee, the first lecture in this program. Guy, is Professor Hershkovitz coming? Okay. So we'll wait for Professor Hershkovitz. Okay, I'm very pleased to have Professor Hershkovitz. May you come straight here? Professor of Mathematics at the Technion, and at the same time, the Minister of Science and Technology of Israel. Please.
Good morning to you all. Well, first of all, Professor Yuan T Lee, Nobel Prize laureate, and the co-founder of the Asian Science Camp. My personal friend, very close friend, Professor Aharon Chechanover, Nobel Prize laureate, and also professor at the Technion, distinguished members of the organizing committee, and dear young students from Asia and Pacific countries, dear guests. In fact, you know, I have a written address, but I think that I won't read my notes, but rather speak to you here. Well, we are very happy to have you here, and I think I could speak hours on the importance of this very, very special event this year in Israel. First of all, as you probably know, Israel is one of the smallest countries in the world, both in area and in population. I think that the whole population of the state of Israel, which is about 7 million people, could accommodate a neighborhood in an average city in China. So we are not only one of the smallest countries in the world, but also one of the smallest countries in the zones, in our zone. Israel is very, very poor in natural resources, although there are some gas findings recently. However, it is, by all means, universal scientific and technological power. And this is very much due to the very unique resource we have, and that is the human resource. Well, like in natural resources, that most of them are deep in the earth, and you have to dig them, and sometimes to handle them before you can use them. Similarly, although definitely not identically, the same holds for human resource. Human resource is there, the potential is there. But to exploit the potential, to really to turn it into achievements, that is a mission and that is a challenge. The future of our world, by all means, is science and technology. And the future lies in the hands of those scientists, or young scientists, who probably do today their first steps in the way for their scientific achievements. And tomorrow will be the leaders and among the Nobel Prize laureates. Asia is a rising power in the world, and the weight of Asia is rising dramatically. As such, the Asian Science Camp is probably one of the most natural places or grounds on which those scientists of the future are growing. Israel has a very special, very special relationships with Asia. This year is the Asia year of our foreign ministry because we celebrate anniversaries, the 60th anniversary of diplomatic relationships with many of the large Asian countries like Japan, China, India. And so it comes together in the right time. But I think that to do it here in Israel, where we struggle for peace, it's more than symbolic. We know that our world consists of different nations, different cultures, different languages, different religions, and those differences, always along the history, have been the source, the cause, the main cause for conflicts in our world. And the history of our world is a history of conflict. One of the prominent rabbis, scholars who lived here some 100 years ago, he founded the chief rabbinate here, used to say that, well, you know, there's no way to avoid conflicts. You know, many of the conflicts develop because of misunderstanding. There's no way to avoid misunderstanding. You know, sometimes I say something, maybe I'm not speaking clearly enough. Sometimes I'm not understood well enough. I'm sorry for that. This hasn't. Sometimes I'm not understood well enough. Anyhow, the outcome is a conflict. There's no way to avoid conflicts. The question is not how to avoid conflicts, but how to handle conflicts. And that prominent rabbi, his name was Rav Kook, who lived here about 100 years ago, used to say that the Bible gives us the formula to handle conflicts. He said that we look at one of the earliest conflicts of history of humankind. That's the conflict between Joseph and his 10 brothers, when they decided first to kill him and finally they sold him. He said that the Bible, the whole conflict developed because of 4 words. Well, 4 words in Hebrew. And the 4 words are Velo yachlu dabro leshalom, which means, and they couldn't speak peace to him. The question is not how to avoid conflicts, but how to handle. And the way to handle conflicts is by speaking. Unfortunately, in our world, there are different languages, and sometimes there's no common language. Well, I've had, as a scientist, joint works with scientists all over the world. And sometimes I cooperated with scientists who didn't speak Hebrew, and I didn't speak their language, and sometimes even English was not a common language. Nevertheless, when we spoke mathematics, we understood each other. Science is the language that bridges over gaps, over differences. That's the language that we converse at. We understand each other, and it's a win-win-win situation. Not only both direct sides benefit from that, but the whole world. So really, science is the bridge is the bridge for peace. And if you look at this, in this wonderful conference that brings together people from so many nationalities, sometimes different languages, but with one aim, to advance our world, to advance human knowledge, and consequently, of course, technology. I mean, this is the key for peace. Again, I would like to congratulate the founders of this wonderful initiative. As I understand now, this year it is the largest Asian science camp ever, and I'm sure that it will keep growing. I would like to thank all the organizers, our foreign ministry, the Nobel Prize laureates that I know that really went out of the way to come and be here with you. And I would like to congratulate you. And I would like to wish you a very fruitful conference. And by all means, we expect you to be the leadership, the scientific leadership of our world very soon. Thank you very much.
Thank you very much, Professor Hershkovitz, and thank you for coming all the way from Haifa in the north. Luckily, Israel is not that big country, so one can do it in a few hours. So thank you once again. Now we'll have a very brief intermission, musical intermission by Orel Oshrat. Orel plays piano since he was 7 years old. He graduated from the prestigious CMDL School for Jazz in France, and currently he is a student in the Jerusalem Academy for Music and Dance in the Department of Composition. The first piece he will play now is the story about Yishai, an original tune by Orel Oshrat dedicated to a friend and a musical inspiration of his. Orel Oshrat, please. Thank you, Ariel Schratt, for the marvelous piece. Ariel will be back later on. It is now my pleasure to introduce Professor Yuan T Lee, our first speaker. Professor Lee has a long history, which for you all participants might be considered as a prehistory, starting much before you were born. So therefore I'll start in 1967 when he moved to Harvard to work together with Professor Herschbach and on molecular beams and the study of the kinetics of molecular interactions, also using mass spectroscopy. Then he moved to Chicago the next year, 68, and to Berkeley in 1974 to the Lawrence Berkeley National Laboratory. Professor Lee won many, many prizes. I will not list them all here, just mention the most important one, the Nobel Prize, in 1986 for the work together with Herschbach and Polanyi for their contribution to the dynamics of chemical elementary processes. He moved to Taiwan back in the 90s and became in 1994 the president of the Academia Sinica of Taiwan. He is very active in many organizations, and recently, as of last year, he is the president of the International Council of Science, which has all the National Academy of Sciences as members of this organization. So he, in a way, the top scientist, the prime minister, the president of all scientists in the world. He is also very active in fighting global warming and promoting reduction in carbon consumption in order to save the future of you all, us all, and the entire humanity. Among many other things, he is also the co-founder of the Asian Science Camp. The first Asian Science Camp was initiated by Professor Lee and his colleague, Professor Koshiba from Japan 5 years ago in Taiwan. And then it took place in Indonesia, Japan, India, last year in Korea, and finally we are here in Israel. Professor Lee was also instrumental in arranging this specific Asian Science Camp in Israel, and I thank him very much for his help and support in arranging it here. I would like, with your permission, Professor Lee, to quote a few words of your colleague, Professor Koshiba, who wrote me these words. Due to my age and health condition, or age and health condition do not allow me to the participation. However, I feel it is my duty to ask you the following. Please make all the people gathering in the ASC realize the very important fact that is, the basic science is the only field in which people of all differences in religion and or in political standings can freely communicate with the truth and the only judge of the arguments. Wishing you success of the conference, Professor Masatoshi Koshiba. With these words, I would like to invite Professor Lee to take the podium and start the first lecture. let me use this time to remind you that we are expecting your questions at the end of the lecture. If there is an urgent question, maybe Professor Lee will be willing to take even during the lecture, but please do not hesitate to ask and to take part in the discussion following the lecture.
Good morning. First of all, I would like to thank Professor Pelletier for a very kind introduction. And I want to thank the sponsor of this conference, Ministry of Foreign Affairs of the State of Israel, and Hebrew University sponsored this organization. And I also want to thank the organizing committee, especially Professor Zvi Pelletier, for overcoming many difficulties to hold the meeting here. We're very fortunate to have the Asian Science Camp this time in a very historical city of Jerusalem. I'm sure you enjoy staying here. And also, I want to mention that Israel is among the most advanced countries in science and technology. I'm sure during the week you are here, you learn quite a bit about what's going on here. As Professor Pelletier and also Minister mentioned that the Asian Science Camp, we're hoping scientists, young and older, could mingle together and exchange some ideas to learn from each other. And at the same time, we hope that the young scientists from Asia will be able to make network, try to understand, try to get acquainted to each other, and hopefully we can work together in the future. And I would really appreciate what Professor Pelletier has done. Before you came here, he already made some connection for the poster preparation students from different countries. I would say you are the first generation in the human history that you are potentially globally connected. You have the tool to do it. And if people from all over the world learn to talk to each other, work together, then we'll have a bright future. Well, this morning I will talk about dynamics of chemical reactions and photochemical processes. I'm an experimental scientist. I explore the nature. I try to understand nature by doing experiment and ask some questions and see something people has not been able to see, to try to get some answers and move forward. So today I want to present to you 3 experimental approaches to see what we have been doing and what one can do. Well, if you look at the human history, it was interesting. For millions of years, we depend on sunshine. We depend on biomass. We burn the wood to gain some energies. But after the Industrial Revolution, things have changed. After the invention of various machines, our desire of using lots of energy become obvious. And we started to dig from the earth the fossil fuels. So at the present time, actually during the last 200 years, almost all the energy human society has been using, more than 80% or 90%, come from a single chemical reaction. It's the combustion of hydrocarbon to make into carbon dioxide and water molecule. And that is the chemical reaction powering the development of human society. As you see, when you look at chemical reaction, generate energy, of course, it's a combination of weaker chemical bond rearranged and form a stronger chemical bond, so energy is released. So here, I showed the methane combustion into carbon dioxide and water. Methane is in the natural gas. If you look at the petroleum, ratio between carbon and hydrogen is 1 to 2. If you look at coal, carbon to hydrogen ratio is 1 to 1. Well, when you mix methane and oxygen and burn it, it will form carbon dioxide and water and release 191 kilocalorie per mole of energy. We also know it is the collision between molecules transform the compound into other compound, so molecular collision will induce the chemical change. On the other hand, if you mix oxygen and methane in the morning, try to cook your breakfast, nothing happens. Methane and oxygen you can mix together, you wait for quite a long time, nothing could happen. It means when you see a chemical reaction, such as methane with oxygen forming 1 carbon dioxide and 2 water molecule, it shows the stoichiometric relation. It will not tell you how chemical reaction took place. If you use the match to ignite it, then you see methane will start to decompose and produce the methyl radical, and combustion will start to take place. And that could be complicated. Methane will become methyl radical, either eliminating hydrogen atom or dimerize it, or add oxygen atom. Elimination of hydrogen, addition of oxygen, molecular decomposition. After millions of processes, you form carbon dioxide and water. As I said, human society depends on this. But human society also has been producing lots of carbon dioxide. We are in great difficulty at the present time. I say great difficulty. I will illustrate in greater detail in the next my lecture in the camp. But what I'm saying is the following. Today, our carbon dioxide concentration is about 390 ppm. We are adding 2 ppm a year. And we know by the time we reach 450 ppm, the global temperature will rise by 2 degrees or so. And when temperature rises to 2 degrees centigrade, our climate will be in great variation, might have a discontinuity, we'll get into great difficulty. That is only 30 years. It means within 30 years, if we do not do anything substantially important, temperature will rise 2 degrees and we'll go into a great difficulty. So this is really an urgent problem. I did spend almost half my life trying to understand combustion processes, look at individual chemical reactions to try to understand what's going on. And now, I spend most of the time trying not to use combustion to generate energy. How can we eliminate carbon dioxide? Today, I want to tell you is to give you a simple example to illustrate how an experimental scientist divide the method and try to understand what's going on. So I take a very simple chemical reaction. Fluorine molecule and deuterium molecule form deuterium fluoride. As I mentioned earlier, collision between molecules will induce the chemical change, but not as we written. Collision between fluorine molecule and deuterium molecule, chemical reaction might not take place. Fluorine has a weak bond, 37 kilocalorie. You can dissociate the molecule. So if you look at this chemical reaction and try to understand what's going on, you know fluorine molecule will dissociate into 2 fluorine atoms, and then fluorine atom react with deuterium molecule. I don't have the laser pointer. I don't know, laser pointer. Well, fluorine molecule dissociate into fluorine atom. Then fluorine atom react with deuterium molecule to form deuterium fluoride plus deuterium and producing deuterium atom. Deuterium atom will react with fluorine molecule and produce another deuterium fluoride and fluorine and that reaction will go on and go on and go on. It's just a chain reaction. So eventually, F2 and D2 will become deuterium fluoride. For a chemical kineticist, for quite a long time, what we wanted to do is to understand the mechanism. It means how many steps would it take to complete the reaction? And then we want to understand the specific rate constant. Each step, like K1, K2, K3, how fast would it be? If you understand the mechanism, if you understand the specific rate constant for every step, it is possible to understand how fast the chemical reaction takes place. But in the modern time, it's not enough. If you look at the fluorine atom plus deuterium molecule, as I have shown on the right-hand side, deuterium molecule is bound by maybe 106 kilocalorie. Deuterium fluoride is bound by more than 130 some kilocalorie. So when fluorine reacts with deuterium, it forms deuterium fluoride. It will release 31.86 kilocalorie per mole. Stronger bond is small, so energy is released. And released energy could go to different kind of motion. Sometimes the excess energy becomes translational. Sometimes become rotational motion of the molecule. Sometimes energy remain in vibrational. So 31.8 kilocalorie per mole release could populate different vibrational energy level, or go to rotation, or sometimes go into translation. This is called dynamics, reaction dynamics, how the energy is disposed of. In the past, we really did not know. So, as I said, I'm an experimental scientist. We, working on the molecular beam method, it's a dream. Dream is to see how chemical reaction takes place. Not by naked eye. We cannot see atoms and molecule. Even you find an excellent student, you will not be able to train to see atoms and molecule directly. But what we can do is to trace the trajectories of atoms and molecule. It means in the laboratory, I can produce the fluorine atom and select the velocity. I can produce a beam of deuterium molecule with known velocity, and I can set it up in such a way I know the velocity of each particle and let it collide at a certain point. Experimentally, if we design an apparatus which will enable you to detect the product, deuterium fluoride, for example, in this reaction. So if I can measure the velocity and angular distribution of the product, it might be able to help you to visualize how chemical reaction takes place. It means we have followed the trajectories. Follow the trajectory and to see how the chemical reaction produced. And that is our goal. In other words, what I'm saying is the following. Sometime fluorine plus deuterium molecule collide, deuterium fluoride will be moving very slowly. It's internally hot. Molecule is vibration, rotation excited. It's hot molecule moving slowly. Sometime reaction produce deuterium fluoride move very fast. Deuterium fluoride itself is cold, but translation energy is high. Total energy is to conserve. So if I were to set up the experiment, crossing fluorine atom, deuterium molecule, and measure the angle and the velocity of deuterium fluoride, keep on measuring it, every time chemical reaction takes place, you measure the angle and velocity of the product. From that angular and velocity distribution, one hopes to visualize how chemical reaction takes place. So this is an experimental challenge. Before we did it, nobody has been able to do this type of experiment by following the trajectory or single collisional events. So we designed apparatus, which is quite complicated. I'm a chemist, but at the end of my postdoctoral period, I became more like an engineer. really designing all sorts of things in the vacuum system which will rotate and mass analyze. Here, I just want to simply say that on the left-hand side, we have an oven, 2 tubes made out of nickel. We put fluorine molecule in there. We heated up the nickel oven to 1000 degree K at low pressure. Most of the fluorine molecule dissociate into atom. So atom will effuse out from the nozzle. We have a defining element to make it into a beam. Then you do have a slotted disc, many of them stacked together. Position is slanted, so when I spin the wheel, only those atoms move at a certain velocity will go through. Atom moving too fast or too slow will not be able to synchronize with the motion of the slotted disc, will not go through. So I can produce the fluorine atom in the vacuum chamber and then cross with another beam. The deuterium molecule is supersonically expanded, well-defined beam with known velocity collided there. And we want to use the detector to monitor velocity and angular distribution. So this slide shows you the detector part. I've shown you how can you produce the fluorine atom with known velocity. Now we pay attention to the detector. This detector is in the big vacuum chamber with a rotating lid. It's rotate. Outside is 1 atmosphere, inside is 10 to the minus 7 tall, but detector could be rotated. And beam across right at the center here, product molecule shown as a red. Thank you. Product molecule shown as the beam crosses here. And product molecule scattered all over the places. And we will detect those molecules in the plane of the beam with a mass spectrometer. It's electron bombardment ionizer, quadruple mass spectrometer, and ion hit the target, generate the pulse electron, and there's a scintillator, produce the scintillation, many photons produced, and photomultiplier will be able to detect the pulse. So we count the molecule one by one. Theoretically, it's a simple experiment, right? You cross beams and detect the product molecule. The difficulty of this experiment is when you mix two gases together, produce lots of background. And vacuum chamber also produce lots of background. For example, if you have a vacuum chamber, you can go down to 10 to the minus 11 tall. But molecule collide and product molecule reach here. It will be equivalent to 10 to the minus 16 tall, 5 orders of magnitude less than the background molecule. So especially when deuterium and fluorine molecule mix, lots of deuterium fluoride will fill in the chamber, 10 to the minus 7 tall. So we do have to have differential pumping. So those molecules go in will be pumped away, and some of the molecules go in will be pumped away. So we have 1, 2, 3 stages of differential pumping, and those molecules produced here go straight through will be detected. So that differential pumping turned out to be most important. It means when you do the experiment, it's not the level of the signal will decide whether the experiment will be successful or not. It's the signal to noise ratio will be determined whether the experiment will be successful or not. So we spend enormous effort to reduce the background gases, and sometimes we use lots of tricks. For example, if you have a deuterium fluoride filled in this chamber, some of the background molecule goes straight through. You won't be able to eliminate those molecules by differential pumping. Differential pumping will be helpful if molecule going from a given angle, bounce around, some pump away, and some of them will go into the second chamber and bouncing around could be pumped away. But the straight through molecule, you cannot eliminate by differential pumping. But on the other hand, it's interesting. If you sit in the detector, every time molecule comes in, you could ask a question, how did you get in? Are you the one I want to see? produced by collisions, or are you the ones which is bouncing around and came back in? I can say that if you produce by chemical reaction, then I want to welcome you. If you bouncing around and come in as a background, then I will not welcoming you. I want to kick you out. But how can you tell? Well, some of the background molecule running around might be kicked by some molecules and get in. But chances are very low. Most of the background molecule will be bouncing around in the main chamber, hit the wall next to it, and then bounce into it. So if you ask the question of those backgrounds which came into the detector, that background molecule will often say, I did not want to get into your zone, but I hit the surface in front of you, and this time it's unfortunate, just get into your detector by bouncing into your direction. So I can set up the policeman to intercept those molecules. For example, if I have a cold plate in front of the detector, mount the cold plate here, then all the molecules which bounce the wall, try to get in, will be trapped by the cold plate. So that will be able to go beyond the differential pumping. So designing the apparatus often very complicated and need lots of deep thinking and tricks. We designed this apparatus about 10 months. Start from the designing and made the construction, go to the machine shop, and finish it in about 10 months. And that is the machine, beam across, producing product here. And this is the detector which can rotate, scan the angular distribution, and velocity will be measured from time of flight method, chop the beam in front, and see how long does it take for the product to reach the detector. That will tell you the velocity. And I talked about policeman sitting behind is a liquid helium cool plate mounted in front. So molecule will not be able to bounce into the detector from the opposite wall. Well, if you design the apparatus like this and reduce the background to noise ratio, reduce the background, then one could do the experiment. If you're patient enough, sit there or measure in one afternoon, and you see fluorine atom colliding with the deuterium molecule and see the product molecule detected, you write down the velocity and angle, and eventually you can set up the contour map, like climbing up the mountain. The higher the mountain is showing the dense, dark area. And in this reaction of fluorine plus deuterium molecule, what you see is most of the product are bouncing from backward direction with respect to the motion of fluorine atom. And so we immediately understand collision has to line up two deuterium atom, and fluorine atom has to line up almost collinearly, because deuterium fluoride has one deuterium in front, so it bounces backward. It's a backward hemisphere. And if you look at the velocity, some of the product moving very slowly is in the fourth vibrational excited state. The second ring, or the third vibrational excited state, energy is in the vibration. And the third one is the second vibrational excited state, first vibrational excited state. Ground state is almost none. It means this chemical reaction produce molecule in highly vibrational excited state, especially vehicle 2 and vehicle 3 is heavily populated. As I said, this experimental evidence shows three atoms has to be lined together. A molecule come from different angle will require higher energy to overcome the barrier. Atom comes with given angle, it will not react with the bounce off unless you have high enough energy. So you can investigate the energy dependence. If you increase energy from 1.82 kilocalorie per mole to 3.32 kilocalorie per mole. Then, as you see, only the collinear reaction will produce the product. Once it backward, now collision with a given angle, reaction is become possible because energy is high to overcome the barrier. So you do see the population, the backward dilation, low vibrational excitation go to higher and higher vibrational excitation. That shows that the energy dependence of the acceptance angle keep on increasing. Some of the product will even move to the forward dilation. So that is one of the simple experiments shows how can we understand the dynamical chemical reaction by following the trajectories. Well, you might want to ask a question. Why do you want to understand in such a great detail? Why? And because advancement technology enables us to use the chemical energy to produce electromagnetic radiation in terms of chemical lasers. So for example, if I have a deuterium fluoride put in the oven, heat it up to 3000 degree K, most of the molecule be in the ground state. First vibration excited state is about 25%. Second vibration excited state compared to the first excited state is again 25%. So if I shine the light, if the infrared photon is adjusted to be in resonance from V1 to V2 transition, because there are more molecules in vehicle 1 compared to vehicle 2, when we shine the light will be absorbed. One molecule will be excited to vehicle 2. And that's the way we do spectroscopy or vibrational spectroscopy or identify product molecule. If I do not put deuterium fluoride in the oven and heat it up to 3000 degree K, instead I mix fluorine atom and deuterium molecule in the flow tube. Then deuterium fluoride produced will be mostly in vehicle 3 and vehicle 4. Vehicle 2 is less, vehicle 1 is even less, almost none in the vehicle 1. So if you look at the vehicle 2 to 2 vibrational state, and now if you pick up the infrared photon in resonance with 2 to 3 transition, because now there are more molecules in the vehicle 3, so when you shine the light, stimulated emission move 3 to 2 will be more than 2 to 3 because vehicle 3 is most heavily populated. So induced emission, computer absorption will be more. So light will be amplified. So if you create a situation like this, then you can use this chemical system to produce the chemical lasers. Population will become equal, but light will be enhanced. So very often, when you ask the question, is this exothermic reaction could be used as a pumping reaction to produce the chemical lasers? That will depend on how the energy, excess energy goes. If you go to internal excitation, it is possible to produce the chemical lasers. Now, I'd move one step forward to look at the dissociation of polyatomic molecule. Again, I want to tell you, we are interested in inventing the new method to look at something which is not easily understood. Because when you look at the polyatomic molecule for the dissociation, you need to understand the mechanism, identification, primary product. And you want to understand the branching ratio, competition of the various dissociation channels. And we also want to understand the dynamic intramolecular energy transfer or isomerization of the excited molecule. Sometimes you also want to know the dynamics of partitioning of extra energy among various degrees of freedom. Polyatomic molecule certainly is much more complicated. So if I take a molecule, polyatomic molecule, in the laboratory, if you put the molecule in there, which is not moving, it's stationary. That's difficult. Experimentally, it's very difficult to produce a molecule which is not moving unless you cool it down to 0 degree, absolutely 0 degree centigrade, 0 degree Kelvin, molecule will be moving. Well, anyway, the molecule is not moving, sitting here. If I shine the laser to dissociate the molecule, if I have two channels, one channel produce M1 and M2, another channel produce M3 and M4. From the momentum conservation, you know that if one of the particles is heavier, moving with a slow velocity, the other particle lighter, which will be move with high velocity. It means in the dissociation process, in addition to the conservation of mass, M1 plus M2 or M3 plus M4 should be the original mass. Momentum, M1 U1, M2 U2 should be the same. M3 and M3 U3 and M4 U4 should be the same. So in other words, sometimes you have difficulty identifying product, but if I know the velocity ratio, if I can measure the velocity, if I don't see the parent ion, when you try to detect the ion already fragmented, but if I know the velocity ratio, I can understand from the velocity ratio, you will be understand the mass ratio, and mass is conserved. So I can identify the product. So this is interesting. For chemical identification, I use conservation of mass, conservation of momentum, and just from the velocity and look at the fragment, I can already tell you what your parent look like, or identify your parents. And so, if I sit in the molecule, see a molecule which is not moving here, then U1, U2, U3, U4, measurement of those species. So velocity will tell you what's going on. But as I said, it's not easy to make the molecule stationary or sitting in a certain spot. But I can produce the beam of molecule moving at a certain velocity. So that's okay. If you can sit together with the molecule and moving together with molecule, and if you shine the light and see the dissociation, if you are moving together with the molecule, you will still see the center mass motion, U1, U2, U3, U4. Like you sit in the airplane talking to your friend. Airplane move very fast, but you and your friend sit next to each other. It's not moving. But from outside, looking up, you and your friend is passing by very quickly. And so, if a molecule is moving, in the laboratory scheme, you want to observe what's going on. What you will see will be M1 will scatter in that direction, M2 will scatter into this direction, M3 and 4 will scatter in different direction. It means in the center mass coordinate system and the laboratory coordinate system, you have to add the vector sum or the moving vector of the center mass of the molecule. But anyway, if you can measure the angular and the velocity distribution, you can transform back to the center mass coordinate system very easily. So experimentally, what we want to do is produce the beam and dissociate it, and have a detector moving a different angle and tune the mass to a given mass and detect where the velocity in the laboratory coordinate system, and I can map out the three-dimensional structures to understand what's going on. And that takes time. So we do have an apparatus very similar to the cross-beam apparatus, except now one of the beam is a laser. Laser, we shine through here. Other beam is rotating. Detector is again 1, 2, 3. This is 4-stage differential pump apparatus. And molecule will be ionized, go through quadrupole mass spectrometer, and count the ion one by one. Now, because of the availability of high-power laser, you can do very interesting thing. If I take a molecule in the vacuum, moving in the vacuum, I say I want to understand the thermal decomposition. Some of you will say, how can you do thermal excitation, dissociation? Because there's no collision. If there's no collision, how could be energy accumulated to such a high energy level. But now, infrared laser will do exactly what collision will do. The reason is the following. If you take the molecule, shine high power infrared laser, you can excite the molecule or stimulate the molecule, the photons from excited state. So excitation stimulates the emission. It will go up and down, up and down. But density of state is higher when you go to a high energy level. On the average, molecule will be going up and down. So that process is similar to collisional process, accumulate energy from low temperature to the high temperature. Well, now you're doing it in isolated molecule. And of course, when you excite the molecule to a certain energy level, molecules start to dissociate because you accumulate more than enough energy to dissociate. This is a molecule called nitroethane. Nitroethane is interesting. You can stretch the NCM bond. It's a weak bond, maybe about 55 kilocalories. So excite the molecule, stretch the CM bond, and go through the concerted reaction from ethylene and HONO. There are two possibilities. Once you form the ethylene and HONO, those are stable molecules. So when you reach the transition state and the electron transfer, you form the stable molecule. So bond disappears, interaction becomes repulsive. So just like explosion, molecules separate very quickly. On the other hand, simple bond rupture, keep on stretching, at the end, enough energy the molecule dissociate. It will follow the statistical processes, will not be like explosion. So this reaction, if you go through concerted reaction from the stable molecule, it will be like explosion fly apart. If the simple bond rupture, the molecule dissociate with very small velocities. And I can use the laser to control the excitation energy level. At first, if you excite up to this level, only concerted reaction will take place. But if you pump it to a high energy, then simple bond rupture will take place. Afterward, it will be competition between these two channels. At the end, simple bond rupture will win the competition because this transition state is very restricted. Only a very small number of molecules will go to that state. If energy is high enough, most of the molecules dissociate into that state. Anyway, as I said, isolated molecule, you can pump by infrared laser and dissociate the molecule. If you take this molecule and dissociate to HONO and ethylene, average translation energy is 20 kilocalories, very, very high. 20 kilocalories means much faster than 747 flying through the air. If you have a simple bond rupture, then translation energy will peak at 0. So you know the simple bond rupture, if concerted from stable molecule, it will explode. That, on the average, moves slower than 747. Of course, now you have the conservation of momentum, and you also have the information about dynamic, whether it's concerted or not. So even a very complicated molecule, so RDX, this molecule is interesting. If you look at this molecule, there's an NN bond, just like a wall, separating fuel, hydrocarbon, and oxygen. So oxygen and hydrocarbon are separated. Very often you look at the rocket chamber containing hydrogen tank and oxygen tank and mix together and burn and shoot up. But this compound, it's called energetic compound, in one molecule, there's oxygen and fuel, hydrocarbon and oxygen together, and separated by nitrogen molecule. Nitrogen molecule is stretched here. After molecule decompose, it bond will become a triple bond again. It will also release energy. So this compound is high energy compound. contain fuel and oxidizing agent. So you rearrange it, it will form N2CO water and release lots of energy. Experimentally, those are the final product. But people did observe HCN formation, HONO, NO2, N2O. This form all of those compounds. So they ask the question, what is the mechanism, dissociation mechanism? Is this a unimolecular decomposition, break certain bond, and then transform to this? What are the primary process? What are the secondary dissociation process? And also want to understand the dynamics. As I said, using conservation of momentum and understanding which are the concerted mechanism, which are simple bond rupture, if you're patient and tune the mass spectrometer and from 120, 74, 102, 81, 74, keep on scanning it. This is the flight time. Sometimes product is moving very fast. Arrival time fast. Sometimes slow, like 102 is slow. Compared to the purple curve, it's very slow. And you're patient enough, measure different angle with different mass after many, many months. You do understand this is really quite interesting. Although Indian bond rupture will compete, but major channel is electron move around. This molecule will decompose into three CH2 and NO2, and then that product molecule will again go through concerted decomposition from HCN, HONO, or N2O plus H2CO, depend on whether hydrogen atom move to NO oxygen and form HONO and HCN, or oxygen atom move to carbon to form H2CO plus N2O. So two consecutive steps of concerted decomposition, more than 60% of the channel goes through these two processes. Other 40% are the simple bond rupture competing. I can say this is conclusion is the following way, but student, graduate student, let's just sit there and measure it, analyze it, it takes more than 4 months. So my question is the following. As I said, as an experimental scientist, we already said, are there better experimental approach to solve that problem? One thing is quite interesting. If you look at the decomposition aromatic hydrocarbon or RDX, once you excite the molecule, energy is randomized. It takes a long time before energy accumulated to the certain mode and molecule decays. And that takes microsecond or longer than microsecond. So if you do experiment, beam is moving, it's something like 10 to the 4 centimeter per second with a heavy molecule. 10 to the 4 centimeter per second, and in 1 microsecond, it's 10 to the minus 6 seconds, and molecule is moving the 10 to the 4 centimeter per second. 1 microsecond is only moved by 0.1 millimeter. So all the thing, energy randomization, decomposition, is taking place within 0.1 millimeter. Takes more than 1 microsecond, sometimes longer. During the time, molecule tumbles, rotate, and originally isotropically distributed. After you excite the molecule, it will be also isotropically distributed. So large polyatomic molecule, when you measure the angular distribution, all is isotropic because molecule has been vibrating, rotating, tumbling so many times. So angular distribution will not give you anything new. It only tells you it lives for a long, long time, isotropic. Well, if that's the case, why should we measure the angular distribution step by step? That is because if I want to know the center mass velocity distribution, you have to go through that. But if you know proatomic molecule, all of them will be isotropically distributed, then I can have a different philosophy in doing the experiment. The philosophy is the following. Okay, we have a beam. Beam, and in the center-mass coordinate system, product will be scattered in different spheres. If I were to do this, I dissociate the molecule here, product will expand and move to the forward direction, and wait for a while, wait until the molecule, which is not dissociating, reach here. It means center mass reach here. If I use a vacuum UV laser to dissociate all the molecule along the diameter, then because it's isotropically distributed, if I measure the velocity distribution along the single line, I will be able to generate the spherical distribution, all the information you needed. So my question became very simple. If I use the vacuum UV laser to ionize the molecule after certain times of the center mass move to this direction, all the sphere will be expanded with different diameters, different radius. Then I ionize. So if I can measure the position of the product, I will know the velocity in the center mass coordinate system. Then the challenge is to analyze the mass produced along the single line. So the philosophy is the following. I dissociate the molecule will be expanding. Then later on, I use in vacuum UV photon to ionize all the product. Sometimes molecule is moving slowly, sometimes moving faster, different cycles. So the position will tell you the velocity. So I should analyze the mass simultaneously. Conventional magnetic mass spectrometer, if you want to measure the line, the magnetic gap has to be wider, fringing field will be high. It's really not very convenient. So with other method, which really should work well, is the following. This mass spectrometer is a different concept. If you produce a beam of molecule and you ionize it, you dissociate the molecule here, and molecule expand, and downstream at a certain time, I have a ionization laser going through here. Then I will accelerate the ion with a very short pulse. It means once you accelerate the ion, and before ion leave the electrode, I will shut off the electric pulse. So every ion will be accelerated for the same amount of time. Not same amount of distance, same amount of voltage, it's same amount of time. So momentum gained by every atom, every molecule will be the same. So if I do this, I pulse the electric field and turn it off before all the ions get out from the electrode. Then all the ions come out from this slit will have the same momentum. So I can set up the momentum analyzer, not the magnetic analyzer. So I have an electrostatic plate. In order to make the experiment convenient, at first we have a very narrow gap, then the gap is widened, electrodes become wider and wider, overlapping the electrode, but the field inside will maintain the same. Just the gap increases, we have a higher voltage and make the field the same. So ion goes in, according to the momentum, it will disperse the different direction because electrostatic field is an energy analyzer. So every molecule goes in with the same momentum, constant momentum. If you have different mass, you will have different energy. So this energy analyzer is really proportional to the momentum square, inversely proportional to the mass, or the mass will be inversely proportional to the energy. So by doing energy analysis, you will be able to analyze the mass. So conventional mass spectrometer, we use the constant energy, accelerate the constant energy, then use the momentum analyzer, magnetic field, to analyze it. That's very complicated. It's not feasible. But what we have done is the parallel plate, electron parallel, and use energy analyzer and constant momentum to analyze the product. And the machine is shown here. One of the laser will dissociate the molecule and ionize it, and then with an electrostatic analyzer and determine the position, and that tell you the mass. It's the energy analyzer as a mass spectrometer. And this is one example. If I take fluoromethylbenzene and dissociate by 193 nanometer, and different mass will show up different energy, so mass analyzer show different mass, and the other axis will show you the velocity, how fast the molecule dissociate and what mass is produced. So in a sense, what we have been doing for months after months, measure the angle, measure mass, and time of flight accumulated, here we can use one laser pulse, signal is high enough, in a few seconds you already got all the experimental result you will be getting all months. Now I show you one example to show you why it is so important to be able to do experiment efficiently. You take the toluene. I don't know how many of you learned enough organic chemistry to know that you take this molecule, you're excited by 193 nanometer, you don't see the fluorescence. Excited energy will go through internal conversion, become heat. Vibrational motion of the molecule goes through internal conversion, so electronic excitation will become vibrational excitation. And if you look at this, CH bond is the weakest, because this electron will be delocalized with the aromatic ring, so this bond is weak because of the stabilization of the radical. And this is high energy. So teacher in organic chemistry will tell you that if you excite the toluene, most of the molecule dissociate by eliminating hydrogen, not as much dissociate by breaking the carbon-carbon bond. What they tell you is true, certainly true. This is based on energetic. But that will not tell you everything, what's going on. So we are quite curious. Will you replace hydrogen by deuterium? If I replace the hydrogen by deuterium, then we'll produce deuterated methyl radical, but hydrogen elimination will be deuterium atom coming out if I deuterate it. Well, surprisingly, when we put deuterium to replace hydrogen, when you tune the mass spectrometer in this region, tune different mass and you measure different velocity, you not only see CD3, you also see CHD2, CH2D, CH3. See all the isotopes scramble ones. If this is a simple bond rupture, how can hydrogen scramble? And you look at the ring, the same. In the ring, hydrogen is scrambled. Either look at the hydrogen atom loss channel or methyl loss channel. In the ring, hydrogen is scrambled. So it was quite curious. How could a simple molecule scramble like this? And when you look into detail, then we realize that when you excite the molecule, goes through internal conversion, it isomerizes. Computational isomerization is as effective as the bond dissociation, and isomerization is from 6-member ring. Methyl will go into it and form 7-member ring. Once you go to 7-member ring, hydrogen atom scramble very, very efficiently. So after scrambling, go back to toluene again and emit isotope scramble species. And so we did learn something new. Early discovery, when you look at the ring permutation in the 60s, in the textbook I learned, it would say if you excite the molecule it will cross bridging the chemical bond and form from 1,2 to 1,3 compound, dimethyltoluene. But we did observe that's really not the right mechanism. It's a methyl going to form semi-membrane ring and then come out again. So here we did see deuterated compound from semi-membrane ring scramble very quickly. And even if I use carbon isotope outside using carbon-13, after scramble it, carbon-13 will go into the ring also. So that amazes us quite a bit. And with this machine, we've been able to investigate dissociation, aromatic hydrocarbon, and go into many interesting things. I don't want to go into the detail of those, but I do want to come back to one of the chemical species, which could be very interesting. At the beginning, I said one type of chemical reaction, combustion of hydrocarbon, provide all the energy of human society. In the ozone hole problem, there's one compound which played the most important role. In the late 70s, Mario Molina, Sherry Roland, and Crutzen is pointed out fluorocarbon once go into the upper atmosphere, it will absorb vacuum UV photon and produce chlorine atom. Chlorine atom could react with ozone very quickly and form chlorine monoxide, and there are abundance of oxygen atom in the upper atmosphere that will recycle the chlorine monoxide back to chlorine atom. So this is called chlorine cycle. If you have a hydrocarbon irradiated by UV photon to produce chlorine atom, chlorine will destroy ozone, go through chains, destroy many, many ozones. And that has been verified. And very quickly, we have the international agreement, Montreal Protocol, and every country agreed that we will not use chlorofluorocarbon as much, banned for quite a while now. But a couple of years later, scientists did observe in Antarctic atmosphere, there's a cold Antarctic lower stratosphere. Ozone is completely depleted. It is an ozone hole. And why is the ozone hole produced? If you want to produce an ozone hole, there must be a mechanism to recycle chlorine faster than chemical reaction shown above. And Mario Molina suggested at lower temperature, chlorine monoxide not only produce chlorine by reacting with oxygen atom, it could form the dimer, COO dimer, and dimer could absorb the visible photon and dissociate quite effectively, and that produce chlorine atom. So dimer is the one which causes the chlorine atom production. There are some other issues, like chlorine atom forms CO2, the dissociation of CO2. What happened? We investigated those questions, especially those are vibrational state specific. I don't want to mention this. This is really very interesting chemistry going on here. Let me come back to ozone hole problem. You see, what Crutzen, Roland, Molina has shown is chlorine reacts with ozone, forming chlorine monoxide. Chlorine monoxide will react with oxygen and generate chlorine atom and go through this cycle. But Molina said if two chlorine monoxide form chlorine monoxide dimer, and that will absorb the photon more effectively, especially in the longer wavelength photon, and regenerate two chlorines. And that is the that cycle is the one which produced the ozone hole. So, how effectively chlorine is regenerated will depend on how effectively chlorine monoxide dimer will absorb the photon and dissociate. And if you look at the dissociation, it was very interesting. In 1990, Burkholder and co-workers did measure the chlorine monoxide dimer absorption cross-section that's shown in this line. The same year, Dumont measured it. He gave a lower number. And in 1995, Harder and Dumont did it again, and they obtained even lower number. In 2007, Pope remeasured it, and his number is 1 order of magnitude less in the 3400. Those are the important area. 1 order of magnitude less than original measurement. And his paper said dissociation of chlorine monoxide dimer is so slow, it should not be responsible for the depletion of ozone layer, or Antarctic ozone hole. So there was a paper published and said chemists poke holes in ozone theory. It means that the Pope's measurement shows that the chlorine monoxide dimer should not be responsible for the decomposition. And if you look at the data, it's interesting. As time goes on, cross-section becomes smaller and smaller, and everybody believes that the science makes progress, so the most recent measurement should be most reliable one. But is that true? Not quite. The reason is chlorine monoxides are radical. When you make the measurement, there are lots of background. So what they are doing is take very large number, subtract a very large number. So the number they obtain has some uncertainties. They always show that the uncertainty is small, but uncertainty might not be that small. NASA at the time said scientists should determine the absorption cross-section of CaO dimer within 50% in the next 5 years. It's a shameful that differ by order of magnitude, 10 times difference, and do not understand what's going on. But in order to do that, we have to do a different experiment. For example, here you produce chlorine monoxide dimer. If you shine the light through, background molecule will also absorb the photon. So the experiment goes through here, will be large number subtracting large numbers. So what we have done is the following. Use the beam method. This is mainly done by my former student, Dr. Lin, Simin Lin. Produce the beam. We have a chopper to chop the beam. So I can check the velocity distribution to identify what mass we are detecting. Then we go through the skimmer, cold slit, and then here we dissociate the molecule. The important thing is, if I use a mass spectrometer to monitor a single species, chlorine monoxide dimer, if I only detect that species, so whatever we do is only related to the chlorine monoxide dimer. There's not, we don't have the problem of large number subtracting large number. So you produce the beam, chop the beam, and detect the species. Chlorine molecule move a little faster in the effusive beam source, follow the Maxwell-Boltzmann distribution. Chlorine monoxide dimer also follow the Maxwell-Boltzmann distribution. So the species we are detecting, we have don't have any question. And then you shine the laser, burn the hole. You see hole burn, chlorine monoxide by adjusting the laser intensity. Then experimental data shows that our data is closer, much closer. We were much more precise than the Burkholder's 1990 data. So sometimes time goes on, people measure lots of numbers and sensationalize published in the science magazine, Nature's, and said, you guys are all wrong, turned out to be not quite so. And so today I just show you that we need to develop new experimental method to answer some of the questions that's not been answered. That's the law of experimental scientists. We are also doing many other things, but I will not continue. Time is up. Well, thank you very much for your attention.
Thank you very much, Professor Lee, for this enlightening talk. I think we still have time for very few questions, so please. Please stand up and tell us your name.
Well, why deuterium, why not hydrogen as an example? Because hydrogen requires fluorine. Fluorine is mass 19, hydrogen is mass 1. Hydrogen fluoride give you mass 20. Argon, double plus. Argon is abundant in the air. Argon is mass 40. Mass 20 is argon double plus. So even you have a trace of argon, will give you background. We've done F plus H2, we've done those, but deuterium, as an example, is no background. No combination carbon, hydrogen, or oxygen, hydrogen will give you 21. 21 is only produced by F plus D2. So that is the consideration of low background. We have done F plus H2.
Speak up, please.
Yes, certainly. Using scattering to get the information. The particle physicists usually use scattering process to from the measure mass and energy, try to understand what's going on. In that sense, this is quite similar. Only difference is we are working on a milli-electron volt. They are working on the mega or billion electron volt. So their detection method, the detection of the particle, is, in a sense, will not be limited by the background. Of course, the signal level could be very low. Otherwise, it's quite similar. Experimental method is similar.
More questions? Okay, over there.
Yes. Because of the air is colder in the Antarctic region, so chlorine monoxide forms dimer more easily. Arctic is also happening, not to that great extent. Certainly, it's because of the circulation of the stratospheric atmosphere. It will have a different temperature. Yes. initial molecule moving at certain velocity, but in the center mass system, if you take the molecular framework, when molecule dissociate, no matter where the energy goes, momentum has to conserve. In the laboratory, momentum is not conserving because you have to add the momentum of the molecule and into the product momentum. So the sum of the momentum will be in the laboratory coordinate system. But in the center mass coordinate system, momentum is conserved.
Okay, I think we'll stop here. I would like to thank Professor Lee once again for this marvelous lecture. I will just say that I'm not sure I understood it all, but I understood few things. One, that you need ingenious but very simple idea of moving molecules and molecular beams to open a new area of research. The other thing is that even if you have simple idea, there's still a lot of work to do of physics, mathematics, building, designing mechanical the apparatus, and tedious work of gathering data and then analysis using mathematics and computer. So it's a lot of work. And finally, possibly the most important aspect is asking the right questions. So I think these are lessons we all should take home from, among other things, from this lecture. Thank you very much.